Have you ever stopped to think that there's a hidden language all around us? A language that describes how pretty much everything in our world works, from the sound of my voice to the screen you're looking at right now. Well, today we're going to decode that secret language. We're talking about signals and systems.
Okay, so this sounds like the beginning of a weird joke, right? What could your voice, a picture, and the stock market possibly have in common? But the answer is actually this incredible fundamental principle that connects all of them. They can all be described as signals. And understanding that, well, that's the key to everything.
So if we're going to learn this new language, we have to start with the absolute basics, right? We have to start with the nouns. And in our case, the nouns are signals. These are the fundamental things that carry information.
Now listen closely, because the most important word on this slide is pattern. A signal isn't some static object. It's the variation, the way something changes over time or across space that actually holds all the information we care about.
Think about my voice right now. As I'm talking, I'm creating these tiny little fluctuations in air pressure. It's the very specific pattern of those pressure changes that your ears and your brain are decoding into words. That pattern, that's the signal.
Or, think about a photo on your phone. The information isn't in one single pixel. It's in the way the brightness and the color change and vary across the entire image. That spatial pattern is the signal that your eyes see as a picture.
And this same idea works for data, too. The daily ups and downs of a stock market index, that creates a pattern over time. That pattern is a signal, and it's what analysts study to figure out what the market is doing. So from sound waves to stock charts, you start to realize, man, signals really are everywhere.
All right, so just like any real language, this one has a couple of different dialects. When it comes to signals, they mostly come in two main flavors. You've got continuous time and you've got discrete time.
So on one hand, you have continuous time signals, which we write as x of t. They're smooth, they're unbroken. Think of a real sound wave moving through the air. On the other hand, we have discrete time signals, written as x of n. These guys only exist at specific individual moments in time, kind of like getting the stock price just once at the end of each week. Here's the cool part. The real world is continuous, but all our computers, they think in these discrete steps.
So how do we get from that smooth, continuous, real world to the choppy, discrete, digital one that computers understand? Well, we do it through a process called sampling. It's basically like taking a series of snapshots of a moving object at really regular intervals. And that one simple idea, sampling, that's the crucial bridge that lets our digital devices understand and process everything from our voices to our videos.
Okay, so if signals are our nouns, we need some verbs, right? We need some action words. And that's exactly where systems come in. Systems are the processes that grab a signal and actually do something to it.
At its heart, a system is really just a process. You can think of it like a black box. You feed an input signal into one side, the system does some kind of transformation on it, maybe it makes it louder or filters out some noise, and then out the other side comes a completely new output signal. Let's make this real for a second. Think about a car. The force coming from the engine, that's your input signal. The car's actual physical dynamics, its weight, the friction from the road, all that stuff, that's the system. And that system transforms the engine's force into the output signal, the car's speed.
So now we've got our nouns, signals, and our verbs, systems. The next step is to understand the grammar. These are the fundamental rules that tell us how all systems are going to behave.
First rule we need to think about is memory. And it all comes down to one really simple question. Does the output you're getting right now depend on inputs that happened in the past?
So, a memoryless system, like a simple resistor in a circuit, is super straightforward. Its output depends only on whatever input it's getting at that exact instant. But a system with memory, like a capacitor, is different. It stores up energy, so its current voltage depends on the entire history of the current that's ever flowed through it. It literally remembers the past.
All right, next rule. This one's about something called time invariance. And the question is this: does the system play by the same set of rules today as it did yesterday? Is it consistent?
Okay, what this really means is that for a time invariant system, it doesn't matter when you do something. The result will be the same. If you go into a big empty concert hall and clap your hands, the echo you hear will be the exact same today as it would be if you did the exact same clap tomorrow. The system's behavior doesn't change over time.
And now we get to the big one. This is a property that makes really complicated systems suddenly way easier to deal with. The question is, does the system obey the principle of superposition? This right here is the heart and soul of what we call linearity.
Now, that definition sounds kind of mathy and complicated, I know, but it really just boils down to two simple ideas. First, additivity. The response to two signals added together is just the sum of their individual responses. And second, scaling. If you double the input, you get double the output. Simple as that.
And this is why linearity is such a game changer. It means that if you know how a system reacts to a few simple, basic inputs, you can predict exactly how it's going to react to any complex combination of those inputs. It lets you break a massive, scary problem down into a bunch of smaller, bite-sized pieces you can actually solve. It's incredibly powerful.
Okay, so we've learned the nouns, the verbs, and the grammar. But why does any of this abstract language actually matter? Well, because it turns out, it's a kind of universal grammar for almost all of modern technology. This quote right here, this gets to the absolute heart of it. A mechanical system, like the suspension in your car, can end up having the exact same mathematical description as a tiny electrical circuit on a computer chip. That's the magic of this whole framework. It unifies all these different, diverse fields under one set of rules.
And I mean, just look at how broad the applications are. These very same principles are being used to process your music, to enhance medical MRI scans, to design the control systems in cars, to analyze the stock market, and even to study the deep structure of the Earth. It's this one powerful, unified toolkit for engineering our entire world. It's just amazing.
So I'll leave you with this final thought. You've just learned the fundamental grammar of signals and systems. Now that you know the language, start looking for it. As you go about your day, what patterns, what processes, what systems can you now see and describe using this powerful new language? You'll be surprised what you find.